Okay, welcome all of you. We're going to start soon. Okay, so it's a pleasure for me to introduce Michela Artebani from the Universidad de Concepción, Chile, and she's going to talk on Cox rings of algebraic surfaces.
Thank you very much for the invitation. I'm very happy to be here. I think it's like the fourth time or so. It's a very pleasant place. So the goal of my talk is to give some panoramic on Cox rings, and I decided to stick to the class of algebraic surfaces. Actually, I will mainly talk about smooth projective surfaces over the complex numbers. Well, the subject of Cox rings has grown a lot in the last more or less 20 years. So I don't want to, I'm not able really to give a general picture, but I think already in the case of surfaces, there are some interesting problems. So I will reduce to that case. So the plan of my talk is more or less what you can see on the right side. So I will start introducing what is Cox ring and try to explain why it is interesting. Then I will tell something about the classification or what we know about the classification of Morid-ring surfaces. And in the end, something about the problem of computing Cox rings. Yeah. So let me start with what is a Cox ring. So a Cox ring is an algebraic object, more precisely a graded algebra, which can be associated to quite a large class of varieties, let's say normal algebraic varieties, we will say over the complex numbers, which are projective, or even more generally, we can assume that the only global invertible functions are constants. And we assume, this is an important condition, that the divisor class group of the variety, which is the quotient of the group of Wahl divisor over the subgroup of principal divisors, we assume it to be finitely generated. So in what follows, again, I will concentrate on smooth projective surfaces over the complex numbers with irregularity 0 to guarantee the finite generation of the divisor class group. So for simplicity, assume that the divisor class group is free, but this is not necessary. There is a more general definition. But let's put this condition. So the divisor class group is just finitely generated in free abelian group. So we can fix a subgroup K of the group of Wahl divisors such that the natural quotient map, which associates to a divisor its class, is an isomorphism. So in other words, we are choosing representatives for elements in the divisor class group in a coherent way. Once we do this, we can define the Cox ring as follows. So it is the direct sum, essentially, of all Riemann-Roch spaces of divisors in K. Okay? So this is of course, it is an algebra over the complex numbers. Well, it is an algebra because, of course, we have a sum here, and the multiplication is just the multiplication of rational functions. So let me just recall. So here, this gamma is the usual Riemann-Roch space. And then, so if I have, of course, if I have F1 in this piece and F2 in this other piece, of course, if we do the product as a rational function, this leaves in the sum of the degrees. So for this reason, the Cox ring is actually a K-graded algebra. So the multiplication is compatible with the grading. So from now on, we will usually say that an element in one of these vector spaces is a homogeneous element, and we will say that D in K, or its class in the divisor class group, is its degree. Okay? So the degree of homogeneous elements is the class there. Okay, so there are, we will see there are mainly two important questions related to this object. But to start with, let me say why it is interesting. And I think the main motivation comes from the following. So assume that the Cox ring is a finitely generated algebra. Then, of course, taking the spectrum of it, we get an affine variety. And moreover, it is very easy to, well, it's easy to see that if you have a finitely generated algebra together with a grading, in this case by K or CL of X, this induces an action of a group on the affine variety, and this group is the group associated to the grading in this way. So if you take from CL of X to C star, so from the grading group to C star, in our hypothesis, this CL of X was free, so this is just a torus whose dimension is the rank of the divisor class group. So this group acts on the affine variety. This is the first easy observation. What is interesting is that there exists an open Zariski subset of this affine variety, which is big, which means that the complement has codimension at least 2. And there is a good quotient for the action of this group, whose quotient is exactly the original variety. So there is a construction, this is what is usually called the Cox construction, which allows you to recover the original variety starting from the Cox ring as a graded algebra plus the choice of this open subset. This open subset Hex hat, I think Antonio will go more deeply into this in his talk, essentially if can be constructed in this way, if you have an ample class on the variety, assuming it's projective, as we are doing. Then you take the ray in the Cox ring associated to this ample class, and you take the ideal generated by this. So the zero set of this defines the complement of this big open subset. Okay, so this is the idea. So essentially, given the Cox ring plus the choice of an ample class, you can reconstruct the original variety by means of this map. Actually, this is a reason why the case of surfaces is special, and it is interesting because in the case of surfaces, it can be seen that the choice of this X hat is unique. So you can really reconstruct the surface from the Cox ring. Okay, so having this kind of map is interesting for several reasons. First of all, since the variety is kind of dominated by this open subset of this affine variety, we have global homogeneous coordinates, which are kind of canonical coordinates. They are not just coordinates given by some projective embedding. For example, this property has been used to study density of rational points on certain classes of surfaces, for example, del pezzo surfaces. Well, the basic example of this, I forgot to mention, is just P2. So if you just take P2, it is an exercise using the definition that the Cox ring of P2 is a polynomial ring. And of course, in this case, the divisor class group is isomorphic to Z. So in this case, of course, X bar is just C cubed. This big open subset it can be seen to be C3 minus 0. And the Cox construction there is nothing but the usual construction of the projective space, of the complex projecting space, as a quotient of C3 minus the origin by the action of the one-dimensional torus. Okay, so this very familiar construction can be done for any variety with finitely generated Cox ring. Okay, so given this, there are of course, two natural problems related to this. So the first one is to classify varieties whose Cox ring is finitely generated. In the literature, these are called Maury spaces for a reason which is quite deep. I will mention something later. And the second problem is try to compute this ring, assuming, let's say, that they are finitely generated, but not necessarily. We would like to find generators or identify their degrees or hopefully find the presentation in some very special cases. Yeah, both problems are quite difficult and open in general. So my goal is to give a kind of taste of both, if I will be able to do, for surfaces, smooth surfaces. Okay, so let's start with the problem of finite generation of the Cox ring. So what happens is that for smooth surfaces, there are essentially two main obstructions to the finite generation. And let me start with the first one. So the first obstruction, I would say just algebraic, and it comes from this easy observation. Assume you have some graded, finitely generated graded algebra, A, so graded over some, let's say, finitely generated and free abelian group, K. Then to this algebra, we can associate what is called the weights monoid. We are assuming also that the algebra to be an integral domain. And so the weights monoid is just given by those degrees where the corresponding piece of the algebra is not trivial. Okay, so you can easily realize that it is a monoid. And the remark is that if the algebra is finitely generated, then this weights monoid is finitely generated. And the reason is the following. So first of all, we can always assume to have a generating set given by homogeneous elements. So assume that our algebra is generated, let's say, by some elements. Let me call them F1, Fr. And this Fi lives in degree Wi. Okay? And now let's take some F in some AW, which is non-trivial. So this one is non-zero. Okay? So since these are generators of the algebra, we have that F will be some polynomial with complex coefficients in F1, Fr. Okay? And in particular, this polynomial will start with some monomial. So this will be some monomial with maybe some coefficient. Okay. So, but then comparing degrees, so we have the degree of this and the degree of this must be the same. And so it must happen that this W, which was the degree of F, must be the degree of this product, which is the sum. It's a combination with integral non-negative integral coefficients of these degrees. Okay, so of course these AIs are natural numbers. Okay, so this shows that the weight monoid is generated by the degrees of a set of homogeneous generators. Okay, well, we can also associate to this algebra a cone, which is just the cone generated by this monoid inside the complex vector space associated to the rational or the real, even it could be, vector space associated to K. And of course, since the monoid is finitely generated, this cone will be polyhedral. So it will be generated by finitely many rays, as you see in the picture in the three-dimensional case. Yeah. Well, so if we apply this remark to the Cox ring, what we see is that this weight monoid, in the case of the Cox ring, is just given by effective degrees. So those degrees where the Riemann-Roch space is non-trivial. And this one, the cone associated to that, is what is called the effective cone of of the variety. So in this way, so the weights cone is the effective cone. So in this way, we recover the first obstruction to the, or if you want, the first necessary condition for finite generation. So if the Cox ring is finitely generated, then the effective cone must be a polyhedral cone in this rational vector space. Let me give you an example where things go badly. So just take, for example, two plane cubics. You can assume that they intersect at 9 distinct points. F1, F2 are the equations of these cubics. Take the pencil generated by those. And probably you have already seen many times that this defines an elliptic fibration on the blow-up of P2 at these 9 points. So if you want, the elliptic fibration is obtained you take the map, which is the projection on the lambda variables, and then you resolve the indeterminacy of this map. And this defines a morphism to P1, whose fibers are exactly the transforms of the cubics in the pencil. And you can also easily realize that the exceptional divisors of this blow-up define sections of this elliptic fibration. Okay? So you have a picture like this. And, well, fix one section, or if you want one of these exceptional divisors, an open subset of the surface takes the structure of an elliptic curve over the function field C of lambda. So you can think of it as an elliptic curve over a function field. And so the remark here is the following. So so you fix one of these sections as the zero, as the origin of this elliptic curve. And if the initial cubics are sufficiently general, it happens that if you take another section, this will define a rational point on this elliptic curve, which is not a torsion point. And so you can take, if you take translation by that point, this defines an automorphism of infinite degree of the elliptic curve. And this can be proved to also to extend to the surface. So in this way, you have if you know that you have an automorphism of infinite degree, you apply these automorphisms to one of this section, you produce infinitely many. So this shows that your surface has infinitely many -1 curves. Now, the final thing is the following. It is not difficult to understand that if you take a -1 curve, or more generally, any integral curve with negative self-intersection, this gives an extremal ray of the effective cone. This is because that class and all its multiples are rigid. Okay, so they cannot be written as a sum. And so they span extremal rays, and so we have infinitely many extremal rays, and so the effective cone is not polyhedral. Thus, the Cox ring is not finitely generated in this case. Okay? Okay, so unfortunately, this is not the only obstruction we have. We have another one, which is kind of more geometric. I recall you that a divisor is nef if it has no negative intersection with all curves on the surface. And it is semi-ample if it has a positive multiple, which is such that, well, the associated linear system is base point free. Yeah, maybe it's not the canonical definition, but it is easier for this talk. And so the following happens. Let's call nef of x and semi-ample of x the cones generated by nef and semi-ample classes. So we have this chain of inclusions. So the ample cone, the cone of ample generated by ample classes, is contained in the semi-ample cone, and this is contained in the nef cone. This inclusion is obvious. Of course, an ample class has a multiple which gives an embedding, so it is base point free. This other inclusion is due to the fact that if you take a divisor which is not nef, then it has negative intersection with some curve, and this curve will be in the base locus of it and of any of its multiples. This is the reason. Okay? Moreover, we know that there is this, so we know that the closure of the ample cone coincides with the Neff cone by Kleiman's theorem, and so we also have that the closure of the semi-ample cone coincides with the Neff cone. So the point here is that assume that the Cox ring is finitely generated, then what happens is the semi-ample cone is closed. And the reason is that essentially this cone, as also other cones of divisors on Maury spaces, have a combinatorial description in terms of the degrees of a generating set. More precisely, assume that X is a surface, and as before, take a set of homogeneous generators F1, Fr, whose degrees are, as before, Wi. Then it can be proved that the semi-ample cone of the surface equals the intersection of these cones, which are the cones obtained leaving out one of the degrees and taking the cone over the others. So you take each one, you leave it out, you form a cone, and you intersect all of them. It is not difficult to at least have an idea why the reason of this equality. For example, if you have a degree which is not in this intersection, it means that there is one, it does not belong to one of these cones, so there is one Wi, which is strictly necessary to write that degree. So it means anytime I write that degree as a combination of the other, I need that Wi. That Wi will be the class of a curve in the base locus, in the stable base locus of that class. So this is roughly the idea. Well, but since it is written in this way, it is a finite intersection of polyhedral cones, and so it is closed. So the semi-ample cone of a Maury surface is closed. And so if we go back to the previous, to Kleiman's theorem, essentially, this says that the semi-ample cone and the Neff cone of a Maury surface must be the same. Okay? So any Neff divisor must be semi-ample. The other inclusion was always false. Okay? And so this is the second obstruction. It is a bit more difficult to give an example where of a surface where the first obstruction where you don't have the first obstruction and you only have the second one. Actually, you have to take the easiest example I know is you take a very general quartic surface and you blow it up at a very general point. And then if you take the tangent plane at that point, the proper transform will be a class of square zero, which is Neff and not semi-ample. And the effective cone of that surface is polyhedral. But since it was a bit more complicated to go into details, I prefer not to do it. But there are examples where we have this obstruction and not the other one. OK, so what is the good news is that there is a theorem by Wu and Kiel, which says that even in more general condition, a normal cofactorial complex projective surface, these are the only obstructions. So the Cox ring is finitely generated if and only if the effective cone is polyhedral and the Neff cone equals the semi-ample cone. Actually, so Wu and Kiel proved much more. So they provide a general theorem which holds in any dimension, which actually gives a bridge between the problem of the finite generation of the Cox ring and something related to the birational geometry of variety. And so there is a characterization of finitely generation of the Cox ring in terms of the behavior of cones of divisors on varieties in higher dimension, but I will not go into that. Actually, the name Maury spaces comes from this general result. Okay? Because, well, this type of varieties have a good behavior with respect to the minimal model program. Yeah, but I choose not to go in that direction, so let me skip it. OK, well, so once we have this theorem, of course, we have translated the problem, but still it's not easy, let's say, to classify this kind of surfaces. let me tell you a little bit what we know. So it is very good that my talk came after Joaquín's talk, because again, it appears a kind of, I don't know if trichotomy, but something similar. So as I said, there is no general classification of Maury-Drin surfaces, even in the smooth projective complex case. But there are some results which show that this classification is naturally done according to an invariant, which is the anticanonical Ithaka dimension of the surface. As you see, this is just the analogous of the Kodaira dimension, but for the anticanonical divisor. Okay? So this is not at all a birational invariant. And this is a number, of course, which can be between 2 and minus infinity. So 2 means that the anticanonical class is big. So for example, we have here toric surfaces. We have Del Pezzo surfaces, or more generally, weak Del Pezzo surfaces. So weak Del Pezzo surfaces are, you can think of them just as surfaces with whose anticanonical class is nef and big, or if you prefer, they are minimal resolution of Del Pezzo surfaces with ADE singularities. For k equal to 1, we have rational elliptic surfaces, as the one we have seen before, the blow-up of P2 at 9 points in the complete intersections of 2 cubics. Actually, so the anticanonical class, if you blow up P2, is given by cubics through the points you are blowing up. And so in that case, you have a pencil. So this is where the 1 comes from. In case K, this invariant is 0, you have the case where the canonical class is numerically trivial, K3 surfaces, Enriquez surfaces, but you can also take, I forgot to put it, you can also take a very general blow-up of P2 and 9 points. This is also a case where the anticanonical and all its multiples are rigid. And finally, the case where the anticanonical and all its multiples have no sections, for example, surfaces of general type. So the idea is that the lower it's this invariant, less we know about the Cox ring. Actually, let me show you a theorem which collects several results. So if the anticanonical class is big, so this number is 2, then we know that the Cox ring is always finitely generated. This is a result by Testa, Varela, Alvarado, and Velasco of 2009. Inspired by this beautiful theorem, with Antonio in 2011, we proved that if the invariant is 1, then the Cox ring is finitely generated if and only if the effective cone is polyhedral, so the first obstruction survives, or equivalently if X contains finitely many -1 curves. Actually, we have even a more explicit criterion, which is that the lattice generated by classes of -2 curves has, let's say, codimension 1 in the divisor class group. Well, if the invariant is 0, we have only partial results when the anticanonical class is nef. We prove that the Cox ring is finitely generated in this case if and only if the surface is either a K3 surface or an Enriquez surface, and the effective cone again is polyhedral, or equivalently if the automorphism group of the surface is finite. Actually, so it is easy to see that in this case, if the anticanonical class is nef and if it is not trivial, then it is not Maury-Drin because the anticanonical itself is nef and not semi-ample, since the k is equal to 0. Okay? But in general, if we drop the assumption that the anticanonical class is nef, this is open. There is a theorem by Antonio Laface and Damiano Testa, which characterizes when the nef and the semi-ample cone coincide, but so we don't have a characterization of Maury-Drin spaces under that condition. When k is equal to minus infinity, even worse, we just have examples. There is a quite recent paper by Kuhn and Lee, if I'm not wrong, with some examples of Moradrin surfaces of general type. But as far as I know, there is kind of no general result. So they take specific surfaces and prove that they are Moradrin spaces, like fake projective planes, some product quotient surfaces, etc. So it's very, very difficult for surfaces of general type. So let me see how. Is there any question?
Why you assume Q that is equal to 0?
Because I want the divisor class group to be finitely generated by the exponential, yeah. Okay, of course I will not go into the proof, but to give you just an idea of why this kind of, let's say, positivity of the anti-canonical class implies that, so gives good properties of, in terms of finite generation, let me just mention two facts. So there is a theorem, which is called base point free theorem, which says that an F divisor is semi-ample if D minus K is nef and big, for example. And this is already very powerful. You see that, for example, if the anti-canonical class is nef and big, you immediately have, applying this theorem, that any nef divisor is semi-ample. Because you have that D minus K is nef, and you only need to have it to be big, you only need to have positive self-intersection. And so if minus K is nef and big, it's enough, for example. Actually, it can be proved, I'm not going to that, but we proved that as soon as the anti-canonical Itaka dimension is bigger or equal than 1, then nef and semi-ample cone do coincide. The second thing, so about the effective cone, so the problem of the polyhedrality of the effective cone is very, very delicate in general, very difficult. We know that when the Picard number is at least 3, it can be proved that the effective cone is polyhedral if and only if the surface contains finitely many negative curves, so integral curves with negative self-intersection. And if you assume that the anti-canonical is nef by adjunction, you can see that these are -1 and -2 curves. So if the anti-canonical is nef, you have to control these two types of curves. You have to prove them to be finite. Okay. So this is more or less what I wanted to say about the classification. So as you have seen in this picture, the case where the anti-canonical is nef turns out to be easier from the point of view of the finite generation. And so it was quite natural to try to say something about the generators of the Cox ring in this case. So let's go to computing Cox ring. How much time do I have? 25, okay. So first of all, when you say computing the Cox ring, of course there are several degrees of, so it could mean to find a presentation. This would be the best thing, but this is often too difficult. So maybe you just want the generators, or even less, you want to identify the degrees of a set of homogeneous generators. And this is what we try to do. Let me observe that by the argument we have seen in the proof of abstraction 1, this one, so this argument tells you even more, so tells you something also about the generators. It tells you that if you take any class which is an extremal ray or an element of the Hilbert basis of the effective cone, the Hilbert basis is just a generating set of the effective monoid, let's say. So any effective class is a combination with the negative integral coefficients of those. So if you take any class which is in the Hilbert basis of the effective cone, then the Cox ring must have a generator in that degree. Okay? Because their classes generate the effective monoid. So you need generators in those degrees. For example, as I said before, classes of negative curves define extreme arrays of defective cone, and thus they produce generators of the Cox ring, meaning that for each negative curve, there must be a generator of the Cox ring with that degree. And, well, in some very special cases, these are the only generators. For example, there is this theorem by Batirev and Popov. I think this was the first computation of generators for a Cox ring of a surface which was not like toric. They proved that if X is a Del Pezzo surface, then the Cox ring is generated by elements corresponding to -1 curves, which are the only negative curves, when the Picard number is at most 8, sorry. And the Cox ring has one extra generator in degree -k if the rank is 9. Okay, so in this special case, with rank at most 8, you have just generators corresponding to -1 curves. Okay?
And does this extra generator appear for every single Del Pezzo?
Yes, for all Del Pezzo surfaces of the, yes, it always appears. Essentially because the anticanonical is a pencil, and you need one more generator for the pencil. Okay. So for example, if you take a smooth cubic surface in P3, the Cox ring has 27 generators. Okay. Relations is all another story. I think there is a series of several papers after this computing step by step the relation. And now this is complete for Del Pezzo surfaces. So we have a presentation for the Cox rings. Okay, so now since I have some time, I will tell you something about what we try to do. So two results. The first one with Claudia Correa Deisler, which is a former PhD student of mine, and Antonio. So we started looking at Cox rings of Maury-Dream K3 surfaces. Well, in the case of K3 surfaces, as I said, these are Maury-Dream if and only if the automorphism group is finite. And there is a classification of these surfaces. It is a classification in families. There are infinitely many families for Picard number 2, and then we have finitely many up to Picard number 19, and that's it. So there is a list of lattices given these families. And we tried to identify the degrees of homogeneous generating set, and we came to the following results. So the key idea, which was behind this, was the following, that in some way, the Hilbert basis of the NF cone had to have a key role in producing new generators. Okay? So we know that the Hilbert basis of the effective cone gives generators, but the idea was that the Hilbert basis of the NF cone also has a key role. And this partially, well, confirmed this because we have been proving the following. So the degrees of generators are either classes of -2 curves, these are the easy ones, or sums of the most 3 elements in the Hilbert basis of the NF cone, or some special, some exception, so some classes of the form twice the sum of 2 elliptic curves intersecting in 2 points. This result is optimal in the sense that we have examples of K3 surfaces where there are generators which are necessary in each of these types of degrees. But in some way, it is not so good because we are not able to say, for example, when we really need to take the sum of at most 3. And in general, the Hilbert basis of the NF cone of one of these surfaces is huge. So computationally is hard. We did it up to Picard number 4 together with Claudia in her thesis, and now she's working on it, but it is not very nice computationally, this result. Okay. After this, we decided to kind of try with the same method, which I will describe in a moment, for rational surfaces with NF anticanonical class with Sofia Perez Garballo, a master student in Universidad de Concepción. And the answer in this case is much better because we proved that the degrees of homogeneous generating set, or again, classes of curves with negative self-intersection, so -1 or -2 curves, elements of the Hilbert basis of the Neff cone in this case. And again, there are some exceptions, which are ample classes of the form minus alpha k plus e, where, well, we have some condition, but they are very special, so they appear. So I forgot to say that, so rational surface with minus k Neff, we have two types. We have this weak del pezzo surface, I mentioned before, where minus k is Neff and big, or we have rational elliptic surfaces, but where not necessarily anticanonical, but eventually a multiple of it gives an elliptic fibration. These are maybe you have heard of them like these M. Alfan pencils. Yeah. For example, you can blow up 9 base points of a pencil of sextic with 8 double points, and you get a pencil, and so on. And these classes here only appear for those types, and where the index is bigger than 2. So the multiple of the anticanonical, which gives an elliptic fibration, is bigger than 2. This result generalizes results in papers by Derenthal. Derenthal already studied Cox rings of weak del pezzo surfaces, but with a different proof, which was more kind of inductive, going down to the, blowing down and connected to the Cox ring downstairs. And so this result kind of is more uniform. And also generalized a previous result by Alice Garbagnati, Antonio Lafaccia, and myself, where we studied Cox ring of extremal rational elliptic surface with a section, so where the case m equal to 1. Okay.
But the previous theorem was for all K3s, not just
for all, that one, yes. Yes, this theorem, yes, I forgot to say, this was for all K3 surfaces, yes. Exactly. Let me give some words and then about the idea of the proof. Of both, actually, of both theorems. And the idea of the proof is this. We use Koszul exact sequence with 3 divisors. So there are these sequences. I will also just tell you the kind of lemma we need, which says the following. If we have, let's say, 3 curves, and if we intersect the 3 of them, the intersection is empty. And let's say that these 3 curves are defined by 3 elements, F1, F2, F3 in the Cox ring. Now, if you take an F divisor and you have those 2 cohomology types of cohomology vanishing, H1 over H2, then using this exact sequence, you get that this map here is surjective. Okay? So if you know that a map of this type is surjective, then what happens is that you know that the Cox ring does not need a generator in degree D, because all elements here can be written as polynomials involving elements in these other degrees, and plus this F1, F2, F3. So if one can prove one such surjectivity, we can throw away this degree from those which are necessary to generate the Cox ring. So this is the key idea. This type of surjectivity, it's a generalization with 3 curves to a result which is contained in the first pages of the book Algebraic Surfaces by Beauville, which is a kind of Castelnuovo theorem. And that was with two curves with this joint support, let's say. So this is just an easy generalization. How do we use this? So we combine this with the idea of looking at the Hilbert basis. So given an F divisor, if it can be written as a sum of at least 3 elements in the Hilbert basis, we can try to play this with this result. And the good thing is that it works because we have a good control on, for surfaces with Neff anticanonical class, we have a good control both on base loci and on cohomology vanishing of Neff divisor. Okay, there is a paper by Arborn about exactly these 2 properties for rational surfaces with Neff anticanonical class. And why is this related to the previous one? Because if the Neff divisor, let's say, is written as a sum of 3 elements, if they are NEF and we know they are base point free, we can move them so that the mutual intersection of the tree is empty. Because we need just 3 curves, 3 representative with empty intersection. And if they are base point free, we can get this. Moreover, what we obtain, if we take our NEF divisor and we subtract some of its, let's say, components, when we write it in the Hilbert basis, we still have an F divisor, and we can easily get vanishing results, up to some exceptions. This is what leads to the exception in the theorem, but it almost always works. Okay? And, well, this is the main point. After this, we are able to exclude the sums of 2 elements in the Hilbert basis of the NEF cone, because we are able, for these surfaces, to completely characterize elements in the Hilbert basis of the NEF cones. Well, there is a very explicit description, and so we can take sums of them, and we can, again, with kind of Koszul arguments, we can show that they are not necessary. I forgot to say that this theorem is much better than in the case of K3 surfaces, because here we can almost always say also when these type of elements are really necessary to generate the Cox ring. Okay? So it is more complete. Okay, this is, well, more or less what I wanted to say. And so some references. So this is the book, Cox rings, which I would say is just a general reference about it. The seminal paper by David Cox. I didn't mention it, but well, it is known that all toric varieties are Moridt spaces, and their polynomial ring is, their Cox ring is a polynomial ring. This is the paper by Wen Kiel I mentioned, and these are some papers I mentioned throughout the talk. So the big rational surfaces, etc.
Okay, thank you.